Okay, let's take a look at our designs. So far, this is our progress. Very ponderously. We have a frame and some angled folded sheet metal and a little bolt up here to hold it all. You can see these corner posts are made from bent angled metal. In this case, it is, there you have a good idea of the shape there. In this case, it is intended to be 1/16 of an inch thick aluminum, 3/4 of an inch wide, and that gives us a sense of scale here that the whole thing from top to bottom is about 3 feet tall. I apologize for the use of imperial units. I normally like to work in metric, but these old drawings are from 1952, and they're all in inches, and it's kind of a pain to try and convert 20 different dimensions in a row while you're working to a different unit system. So inches it is today. So the Fusion 360 is, it's been a long time since I used this, so it's basically relearning it from the ground up. So at the moment, just to show our progress, these parts are kind of, I've just dragged them to reasonably relevant positions in space. They're not properly like digitally linked to each other. Like if I drag one, where's the move tool? Things to learn. How do we move things? Bodies. 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 Body one. What's that? Let's try. There's a leg. That's like the master leg, and it is repeated 4 times, 3 other times. All right. Oh, there we go. Move, copy. Move object bodies. Interesting. So there'll be a lot of puttering around here, false starts, and we'll go look at some YouTube videos and tutorials from time to time. This is kind of a casual chat. Feel free to ask questions. Not sure, do you see that chat window there? Oh, you do. You can watch your own chat. So let's start out with a little bit of action, though. Make things a little bit more interesting and get some progress knocked out. This is the set of drawings we're working from, again from 1952, from a high-altitude balloon research project that was done by General Mills and covered a huge variety of technical challenges, just trying to figure out ballooning back then in the 1950s in the United States. So this project is basically sheet metal, which back then would have been the absolute cheapest way to make hardware. We can see here, these are pictures of the final product. Let's rotate this right. There you go. You get an idea of basically a frame. Interesting, it looks wider than in our rendering. High voltage, don't know what that was, but it looks crazy. Various iterations of it through different flights. Pre-flight 1531. One of the tricky bits that I'm not sure of how to do is this this kind of corner patch. Maybe hard to tell, but it's got a very gradual sweep curve from the horizontal bar up to the diagonal bar. And that is it is specified here, as you can see right here, and I drew that much out, and I figured out how to fold it down the middle, but I don't know how to do that sweeping curve that you can see here. It makes that sort of a corner patch that follows the curve of the upright post here. You can see there's a good view of both the upright curved and the patch, the corner patch there. So today, I think let's start with one of the simple sheet metal parts down here. These are kind of fun and should be really easy to build up.
Was this the carrier payload?
It was indeed. It certainly was. And this would have been a scientific payload. Let me go ahead and pull up the paper itself, and we can take a look to see what they were hauling with this thing. Sponsored by the Army, Navy, and Air Force. Progress report, 1952, confidential. Oh, that's awesome. Blah, blah, blah. All the people in the game. So they looked at balloon shape. They looked at calculations of how to understand what the balloon would lift, how much it would lift, how far it would go, what the stresses and the payload capacities would be. This was really in the baby stages of ballooning. Derivation of equations, we'll probably skip those today. Those are a little dry. Cylinders again. Cylinders are super easy to build, but they aren't great at efficiency. Once they start getting longer beyond a certain amount, they actually start lifting less and less payloads. So whereas a traditional balloon like a sphere or a teardrop, as it gets bigger, generally it lifts more and more. A cylinder has kind of a limit, and then it starts lifting less and less because of its geometry. So these are what, by the way, what balloons look like at launch. What did they carry? So it's probable that natural shape balloon for a specific requirement. That's pretty. I'm looking for the instrument package that they carried to answer your question. These are probably photos taken in flight, looking up at the balloon, probably from the rack that we're building, probably had a camera pointing upward. There's wrinkles, or actually that kind of looks like a tear. Hard to tell in these old photocopies. Methods of attachment. This is a wonderful paper to learn how to do ballooning. So let's see if they have instruments. Oh, how to measure pressure going into a balloon. I'll cover all this stuff in future. Beautiful technical shot there. Future episodes, so to speak. For the moment, shape measurements, launch tests, hangar launch tests. That would be impressive to launch an aircraft hangar. A lot of pictures here. I hope someday to get like the original non-photocopied version of these papers, because these were probably beautiful crystal looking balloon surfaces. Gosh, I forgot how long this paper was. It's very long. Let's skip down further. Man, I need to read this thing cover to cover. There's so much good stuff. Instrumentation. Here is the answer to your question. So I'll skim through here briefly. I know you've only got 720p of visual, a little bigger. Okay. So the balloon required a balloon valve and a packaged ballast dropper operated by radio command. The ballast dropper and the radios would be on this frame. The transmitter to send down all of the data like altitude and instruments, probably temperature sensors and pressure sensors, would have been on this rack. A radio receiver. Here's about the gondola, as they called this payload. Another important development in this period was that of a small gondola for lightweight flights. These gondolas were less than a quarter of the volume of our standard gondolas and therefore could be used only for basic minimum flight control and telemetry equipment. No experimental or developmental apparatus could be contained in them. The weight of these gondolas complete is roughly 1/3 of a similar large gondola. So we can imagine the regular gondola must have been about 9 feet tall. Pretty decent, but these balloons are pretty darn big. A third development was that of a pressure-operated sequence ballast dropper. I see John pinging in to note Restream. That's actually what I am using is Restream.io right now. We're zipping out to 3 different services. Another new development was that of a recording device to keep a record of the gondola of telemetry signal in case the radio was lost in flight. The signal was recorded on camera film. Mind-blowing. They had no way to record data back then from sensors that was electronic. So literally the best way for them to record things was with a mechanical arm that was basically like a meter needle that would swing up and down. You could use it out of a meter. And there was a little light on the end of it basically in front of a camera. And as the pressure rose or the temperature changed, the meter needle would swing up and down. And the camera would see this as a light moving back and forth. And the camera film would just creep forward continuously. And the end result was you would get a graph traced up and down on the film. And you could do this with multiple lights. Like you could have several stacked side by side and have like multiple graphs doing different things. And such a neat hack back then to get data stored when you could barely get data electronicized for transmission. Flight equipment contained in gondolas. What a great question you had, Tim. This is literally everything in there. I did not expect this. So we see blinker beacon here. Whoops, okay, you're just gonna have to follow my cursor unless I have a highlighter marker upper here. Draw. Blinker beacon. Blow down box. No idea what that is. Cameras. Triangles. Telemeter film recorder. Baro thermograph. Don't know what that is, but baro usually means barothermograph, yeah. Usually means pressure, and thermo is temperature, obviously. So maybe that was just a combination temperature sensor, pressure sensor. Ballast dropper. Ballast is what will keep you from sinking. Ballast tank, recorder, and transmitter. So the ballast tank was probably holding kerosene or alcohol, and the ballast dropper was probably the like a valve to just open at the bottom of it on command. Balloon valve would have released helium either by command or to automatically control altitude. Yeah, isn't it? Signal coder, that would be actually what converts the data signals into like Morse code. Distribution box, strobe flasher. What the heck is the difference between a blinker beacon and a strobe flasher, I wonder? Photo recording ammeter, again, a meter that was in front of a camera. Thermistor photo recorder, again. Cosmic ray plates. So basically film in an envelope that they were hoping to get little streaks on from cosmic rays. Awesome. Now, let me answer a question I had in the infinity room, apparently. Okay, so it was an interesting little history. Thank you for asking that. I didn't actually pay attention to what this was used for. It was just the first dimension drawing I came across the other day looking through my PDF library of thousands of records and balloons. So let's pick our part. Want something, oh, okay, look at this, lots of holes. Those holes are always fun. And some folds. And looks like the folds are not too complicated. We will have to, no, we can do this. I know how to do this. The problem I usually have is when there's a fold and then another fold, like 3 folds in a row that are like going to take you out up into a 3-dimensional shape. But this we can do. It's just a bottom and 2 walls and tabs. Awesome, let's do it. So we're going to break this up into little drawings so that we can actually insert into the CAD program and and then trace, basically, which is such a handy feature for these old ass, super blurry drawings. So let's do, let's do new drawing here. New design.
Hopping into work. Bedtime for me. Have a good sleep. Set alarms and don't stay up too late.
Thank you. It is just the start of my day. But enjoy, John. Thanks for stopping by. You gonna leave it on while you fall asleep? I have to say, I'm very much enjoying the text-to-speech of the chat in my ear. It's very helpful to actually catch when people chat. So we've got a new drawing, new design. So we're going to insert a canvas, which we will make a new picture for. Export. "1952 May box." A number here. No, we'll just say number 1.
Oh, that watermark isn't bad at all. Oh, guess you'll have a long day ahead. See ya in 8 hours.
Yeah, I'll be here. So have a good sleep, John. Okay, so we've got a picture of this ready right here, separate image. Now let's go suck it in as a canvas item. Nay box 1, and Nay is just the main author on this paper. Okay, so canvas, and it wants to know what part of the world, what direction we want to lay this on. And because this is not like a standing up part, this is going to be a box that sits flat on the ground. Or at least we're going to start with the bottom think it's the bottom. We'll just put it on the bottom and we can work from there. If it's not correct, it can be changed. So we see it's really tiny in the world. I'm going to leave it where it lay for the moment. And what we're going to do now is tell Fusion the real size of stuff on this drawing. So we'll find the largest length dimension line here. Let me close this so you have a better view. Ooh, come on, don't be weird. You're being weird. It's very weird. Okay, let's top. Okay, there we go. We're going to find the longest dimension line, and then we're going to tell it how long that is. And these papers, again, are in inches. So this will be 4 inches from end to end on this cruddy ass line, as most of them are, which to me makes it a fun challenge. It feels like I am working archaeologically here to decipher these hieroglyphics. A lot of times the writing is like, what? That's actually a good one. You can tell it says body drill, if you knew kind of what it was going to be. So let's do a canvas, calibrate, pick a point, bing, pick a second point. We're going to tell it 4 in, and away we go. Now we're real sized in this little world here. So let's just bring our origin back. And for origin, we'll just, let's pick a point here. I'm not experienced enough to know what the best place to throw the origin is for these components. This is really acting weird for rotation. Maybe a corner. There doesn't seem to be a common point that things are dimensioned from. Oh, wait. Some things are dimensioned from the center line. A bunch are dimensioned from this hole. So let's use this hole. Oh, wait a minute. The outer dimension of this box is not shown. So we need to go, let's go digging. We need to find the outer dimension of this box from that drawing. So we've got one bit of it. Ah, I see. So there's our outer dimensions. Let's copy this now with a rectangular selection. I'm not going to miss anything. I say rectangular, please. There we go. Copy new, export. 1952, nay, box 1. Let's call it box 2. Insert canvas. Let's hide this canvas because we're probably going to lay them fairly on top of each other. Insert from my computer. Oh, I saved it as the wrong format. Easy to do. Export as PNG. Save. There we go. Nay box 2. Face. I'm going to do the same floor face there. Now we'll do our calibrate maneuver. Okay, so this is much wider, 14 inches. So we'll do calibrate. By the way, for any new viewers, I will see chats and will respond to you if you're on any of the platforms, YouTube, Facebook, Twitch. Feel free to drop a note if you have a question or comment. So this is 14 inches end to end. Right, 14 and zoom out, way out. There we go. So let's try and find a good origin point where most of the dimensions, or many, are coming from. Well, we've got chained dimensions, which, yeah, in this day and age, it's all right, but it's not the best practice. Yeah, like this outer dimension actually references the outer edge, but nothing else references the outer edge. It just says it's a ½ inch. Really, I don't see any lines that are referenced by more than 2 dimensions. So well, let's just we'll just put it here. That makes everything negative. Yeah, so what? Okay, we're going to edit this canvas and drag. I don't know how to like move this drag handle so it's closer over here, but maybe we'll look that up. Okay, so our origin is move it, move it, move it, move it. Let's try nudging this down a hair. Up. Man, this is really creepy. I've not actually done this numerically before, so this is a new little exercise. I usually just drag it. Yeah, it looks good. Yeah, looks good. So as we zoom out, we can see how this green line, I know it'll be hard on the stream, we can see how the green line lines up with the drawing vertical line, and that's pretty close. So I don't think we will adjust the rotation here. Hit enter, and let's go ahead and save so we don't lose our progress. 1952, nay, box. Okay, let's close that for now. Boop. Okay, so now is the fun part. We get to start drawing willy-nilly. I wonder, let's see if there's any particular good scheme to progress through the drawing with. Oh, you know what I did? I put the origin down here on the dimension line instead of up here at the intersection. Let's tweak that back up where I'd like it. Oop, it didn't go anywhere. Let's see how we did. We could stand to bump Charlotte. And again, this doesn't have to be precise. It's just nice if you have OCD. I mean, I don't think it has to be precise, but okay, now we use one axis. That should be a little more sane. Yeah, that looks great. Okay, so we could start here and just work our way all around, all the perimeter, which is where we'll start. Is there a mirror? I mean, the left and the right are mirrored. Yeah, let's try that. That could be fun to mirror the left and the right. Actually, it's mirrored in quarters. So hell, let's go crazy here. We'll just do 1/4 of it and see if we can replicate it automatically to the other quarters. So in that case, we'll start here at the middle of the side. L for line. Or let's say, oh, let's turn off snapping. And again, these clicks don't have to be accurate because we will actually tell it the dimensions, the coordinates of each of these corners later, which will correct for any inaccuracies. Like we can do like that, and you'll see it will come back in line, so to speak. I like puns, wordplay. Close the line. Okay. So we already have some constraints that it auto-applied, one of which is this line is vertical with the world, and this line is perpendicular to this line. Oh, I see. The constraints that match are blue or dark blue. So if I click this, yeah, this one is perpendicular with that one as well. Okay, so let's start with this dimension here. So we'll hit the, let's hide our origin. We'll do the D key to do dimension from there and to here, which we see is, what does that say? 4 3/8? Yeah, I think that's 4 3/8. Let's throw that in there. So another nice thing that CAD programs do is they will do a little bit of math for you. So if I just type 4 3/8, you're like the old days when people used crazy fractions everywhere. Okay, that's a little odd, but oh, how high is this corner? Okay, we got to back calculate it from this dimension. So this will be 5 3/8 minus 4 3/8. That would be 1 inch. So let's do this dimension to the origin now. And we'll say 1. There we go. What? Man, this is getting all wonky. Let's back up here for a minute. I might have done this wrong. Let's do here to here. That is 1 inch. Okay. And is there a reference for this dimension directly? No. We do know that it is 45 degrees from the indication over here. So by that, with some simple math, well, actually, you know what? Let's just do it literally 45 degrees for a dimension to make it kind of fun. We'll click this line and then this line and give us a 45. I think right on the line. And then we know this one is already on the axis of the world, so that's great. Now that leaves us with the length of this one. So what is the length of that? Well, that's interesting. I wonder why they made this dimension. Oh, it's, never mind. I know why. So what is this? Oh, oh, I did something wrong. Let's go back here to this dot. This dot is going to be not 4 3/8. It's going to be 5 3/8 divided by 2, because we're halfway between here and here. So 5 3/8. 5.375. I getting too far ahead of myself. Will it do compound math? Yeah, it did. Look at that. Okay, so that's not quite on the line, but again, these drawings can be distorted by the scanning process, etc. And so our numbers are what really drives what the accuracy is going to be of these things. And they may not match the drawings, but the numbers are what we would go on for doing this sort of work. So this length here, we don't know and we don't need to know, because we have this 45-degree angle and we know that it intersects the axis. And so mathematically, the program can calculate this triangle having 90, 45, 45, and 1 inch of the side. It knows this side will be 1 inch. So if we place this dot here, that means it knows where this coordinate is, because it knows this is 1 inch. And if we tell it where the other end of this line is, it will know the total length of this line segment. So we have 1/2 for this gap and 3 1/4 to this fold. So that would be from the 0 origin of the world, we have 3 and 3 3/4, 1/4 plus 1/2. Doot and doot. 3.75. Okay, and now we want to have this little peak dimensioned here. So, the angle is 25. And how deep is this fold? Does it go to that intersection? No, it looks like this only goes into this fold on this panel. So how thick is this panel, this fold? Here we have references. 3/8? 3/8? Let's call it and see if it fits the lines roughly. So we'll say the length of this is going to be 3 divided by 8. Thank God I don't have to do these calculations literally. And we know this is going to be straight up and down. So let's add a constraint. Constraints are fun. Horizontal, vertical, relative to the world. Think. See, now it has a little constraint icon. And it's turned black, which means the program says, I now know everything there is to know about this line. I know where it is in space, up, down, left, right, and what angle it's at, because it knows this is on the 0 line, and it is 3 3/4 inches from the 0. It knows the top because it is horizontal, or it is perfectly vertical. It knows the top point is directly above it, and we told it how far directly above it. So line solved. Now let's throw a 25-degree angle in here. I don't get to do angles very much, and they're fun. And again, feel free to drop. Oh, that doesn't look right, does it? Does it? Is that really 25? There's a smudge. It really looks like the same as 45 on the drawing. Do you have any other clues here? 25. Can that be 35? Man, it looks like 25. That really doesn't look like a 45, does it? No, it does not. I mean, back then, you didn't have like exact, easy to do angle measurements. They might have just thrown a visual 45 in there and said, make it 25, because manufacturers would always go by the number dimension over the visual appearance of a part. So Let's just leave it 25 and see what happens in the future of this design. See if that that succeeds. And what happens to all this? So where does our part end, our line end over here? Half of 6.5. So let's do, we'll click the whole line, give us a dimension of 3.25. Half of 6.5 is 3.25. Oh, I did the wrong dimension point. See, the 6.5 starts from the fold line. So let me clear that dimension. Let's do from here to here, 3.25. Look better, more centered? Yes, that looks much better, more centered. So ideally, I want this whole line to turn black, but it's still blue in most cases. So we've got to figure out what data, what information is missing. Let's throw a horizontal on here. No, it's over-constrained. Over-constrained means it's already got information enough to determine that it's horizontal based on this little t. Okay, so angles, 45 we know. We know this is 1 inch. This is 2 inches. Okay, so let's start here. Why does this not know? What does it not know about this? If it's vertical, it should know the angle in space. Let me lighten up our canvas here. So this is a little more vague so we can see our lines better. Let's think about that. I'm going to go get a snack and be right back. How do I do that without making this crazy for you? Restream chat. Sorry. There we go. So I have a BRB icon. BRB. There we go. Let me just check the streams are healthy here. I don't rightly know how to check that on my phone. We'll just assume we've got fun people on Twitch. That's enough for now. This is my first time multicasting. Kind of a test. It's casual. So I had an idea while I was eating a hard-boiled egg that my assumption was wrong in saying that it knew that these vertical lines and horizontal lines were on the axis. So let's tell it explicitly that left and right, it's on this dot. And here, up and down, it's on this dot. So for that, we will use, make sure I turn that little bubble off. Hide. Sorry for the infinite mirror view for a second there. I'm kind of new at streaming, and I'm also on a MacBook Air traveling, so it's a nice challenge for minimal stream management. So let's take a dimension now, add a dimension on this line. I'm missing something. Something's not right. Something's not right. Edit sketch. There we go. So let's constrain it coincident with this point. Hey, that's what I needed to know. Let's do it again. Coincident. There we go. And one final coincidence. All good. All approved by Fusion 360. All black end to end. Great. Good job, everybody. So let's bring Twitch back up so I can see. Keep an eye on that particular stream. I do know how to keep an eye on the Twitch stream from the phone. I see plenty of bots and a couple of real people. Glad to have you here. As my learning the streaming process is going along. I appreciate having somebody to stream to. So now we have our profile. Let's add our folds. Let's see if we can go all the way and put our fold lines in here. Be bold. So this dotted line in the middle is not a line that's going to be acted upon when making the part. As you could see, Though it's hard to tell with this old splotchy drawing, there are dot interruptions in the line. And what that means, excuse me, is, is that it's the center line of the part. So any dimensions that go to this line, you know, are going to the center reference. So they will be equal length on both sides of this line. Let's turn our origin off. It's kind of noisy. Let's turn our dimensions off as well and our constraints, so we've got clean space to work in. Let's go with a line again, but we're going to call it a construction line here. So because these dimensions show this line and this line, because they're both a ½ inch from the H edge, that indicates that indeed this intersection is the halfway point of this cut corner. So we're going to allow this little green triangle to snap our first point of the line, as it's going to start there at the halfway point on this diagonal. So now we will take it up vertical and we'll drop it in here anywhere. Later we'll tell it that it's equal height from this dot. Let's do it again here to here, and I do that good. And then we'll do it again from here up to here-ish. And we'll call that good too. Do we get, oh, we have another one down here. How does it, oh, the peak of this thing is where it's starting from. Looks like that is the correct indication. So we'll then drop that there. So it looks like we may have, do we have all of our lines in this quadrant? I think we do. Let's set these construction lines that are dotted to the appropriate height here. Let's constrain them. Maybe vertical with this one to that one. Yep, that did it. And then this one to that one. Knock that one in. And for this one, let's tell it, okay, so we have 4 3/8 from the end. So let's throw that dimension in. Even though I don't like to reference non-origin sort of points, we'll just sort of replicate the drawing a little bit. Oh, but that's not the line length. It is, why is this? Let's try making this coincident with that line. Would that do better? Yeah, okay, so that, all right, it's happy now that dot is gone. We'll make this one line up with the black dot. There we go. No dimensions needed. We just told it how these were supposed to relate to the existing bits and pieces. Stand by, I have a conundrum for what to do with this tea bag. Tea, Earl Grey, lukewarm. Okay. Now we're going to try and replicate this, mirror it in a 4-quadrant pattern. Let's save. First quadrant. Create rectangular? No, circular pattern. I know it's counterintuitive because we want to actually rotate. We want to actually create these around a center point, not a grid, so to speak. We should put the center point in. Sketch. Can you make a point? You can. Beautiful. Just drop that in there. Oops, not there. And let's coincident that, or vertical that. That. There we go. It's happy. I'm getting better at this, at figuring out what the proper command is. Now we will circular pattern. Objects, we want all of the above, except the origin. Do that. Oh, whatever. Spacing all the way around. Center point. That. Oh, you know what? We don't want that selected. Maybe a little new at this part of the game. It looks like we've probably got everything we want. Center point. Here. Oh, sure, why not have? Interesting. Why are they all construction lines? Oh, interesting. All right, maybe we need to do mirroring, not this. Because they're not symmetrically, not rotationally symmetric. It is a double mirror pattern. So we should put a construction line on the center line. We should replicate that center line. So let's go back to line type. We still have construction set, which is great. So we'll put one through all these points here. Actually, you know, I think there's a line type called center line. No, that's fine. Doesn't matter. Let's try mirror. We should have a center line going the other way too, so that we can redo this command. Doot. Mirror. Objects. Okay, let's undo that line. I want to mirror across that. I guess we can undo these points. I'm not really sure the relevancy of having the points copied versus not. That point just wants to stay. That's fine. We'll find out what happens. Mirror line. Hey, look at that. Looks like our vertical dimension is a little stretched in this sketch. We'll correct that in a moment just for OCD fun. Okay, now let's mirror it again. So I'm just going to mirror all of the points and the lines. Mirror line. Oops, I got to unselect that. Yeah, it doesn't want to mirror on a line that's in the sketch. Hey, look at that. Was that easy or what? So let's remove these little dots, can we? No, that's all right. Look at that. How fast was that? I think if we change like this angle here, I think the other ones will change with it. Hmm? If not, I think there's a way to do it. So let's just try that, just because it would probably be important to be able to know this and do this later. Well, lots of constraints. Wow. Whatever. This is the one we want to change here. Let's call it 45. Hey, look at that. All of the notches here changed, which is exactly what we wanted. 45 degrees. This is looking good. Real good. Look at that. Hey, that's pretty darn cool. We're on our way to making an old 70-year-old balloon device. Back to the future. Okay, so this is definitely a landmark to save. Full pattern. I like it. I like it. It's not really that interesting from the side or anything, but now it's time to start making it interesting from the various angles. We're going 3D now, folks. Sheet metal time. While I knew CAD for many years very casually, never did I work with sheet metal. So this is kind of exciting new skill. And I normally would have looked down upon sheet metal as an old inferior technology, but you know, I'm coming to the realization that it may have its economic place, particularly since it's easy to make cheaply, like a cheap machine shop, or even you could make with a metal bender. Okie doke here. So the first thing, if I recall, was to turn this whole thing into a flange, they call it. And we're going to make that a new body. Aluminum. Man, why is that so? I wish this would go wider. But it won't. I happen to know what the deal is. The second one is aluminum by the inch, which is what we want. Look at that. We now have a piece of aluminum. Let's make sure our sketch shows up on the surface, the top surface. It's kind of hazy. It's clear. All right, so we are indeed working on the top. Let's go back right side up here. So let's take a look at our picture and see if there was instructions for the bending. I'm not seeing any. Yeah, that's just a number. Material is 14 by 5 3/8 aluminum, so that's the outer dimension, and then 052. That's probably thickness. Not sure what that means. If that's thousandths of an inch, that's really thin, really thin. It's like razor thin. But what is that in millimeters? 0.00152 in 0.13 millimeters. Yeah, that's 1/10 of a millimeter. Ooh, that's razor thin. You'll cut yourself. But we'll see. Thickness isn't so important to us in this exercise. Let's bend. Let's bend. This is kind of the fun part. Now we create a bend. We want so now we have to pick two sides of the bend. So in this case, let's do all of the little edge pieces first, we want to work our way in from the outside on the bends. So let's do stationary. We'll do this part, and then the bending side would be, we want to do the mirror bending thing. Let's see, does this look right? Yeah, look at that. We got a little bend. So for the moment, we will assume that they're 90-degree bends because I didn't see any references otherwise. So let's do, actually, you know what? I think we might be able to do all of these. Did they bend along the right lines? No, they didn't. Let's undo that. All right. This is the part we're still learning. So, okay. Corner relief, override. I suppose we could have done this, just one corner and mirrored it. But we'll do what we've got here. Let's do another bend. Stationary, and then this. But I don't want it to do all of that. How do we tell it not to? How do we do that? Maybe we have to split the face. Oh, wait. This has got to be a cut. That's our problem. That's a problem. That's got to be a cut. Exit bend mode. Let's take line. Line, please. This is a little trickier. I'm not quite sure how to do this. But let's find out. Let's do a normal line here to here. We'll call it good. And we want to say, cut this in the body part. We're going to end the sketch. Now we're going to go to the body, sheet metal, and modify. Create. Assemble. Fillet, chamfer. Let's undo the create. Yeah, create the body thing. We're undone. Now we have our line here. Let's redo create with that line in place. So create flange. Oh, afraid of that. So okay, we've got this here. Let's try and bend that tab and see if that behaves better. If it behaves like a split in the material. Oh, damn it. It does not. It's highlighting the whole thing. Maybe we need to put a gap here, like an actual sensible, like we have more than one atom split here. Let's do that. Edit sketch. Let's go back on our timeline. Okay, yeah, so if we edit this, let's cross our fingers that everything changes. So we'll cut into this side, I think. Or would it be better to cut in here? Yeah, I think it'd be better to cut into the longer side. So let's do a line here to here, then one over to there. And for our, do we get duplicated? Cross fingers, maybe? No, that's all right. I'll be lazy and just do it 4 times. Let's do a dimension here to here. Say 0.32. That's fine. And we'll delete. Oh, we need to split stuff up here. I think we need to split it. Let's just try and yeah, let's be good about this here. Delete. Hey, that worked. Hey, there we go. We just have to break the loop. Let's turn this into a construction point. And this, I would make, let's, I know, let's extend the construction line here. No, not like that. L, construction line, down to there. And we need to get this point to go over there. And just split this and then delete that is what we need to do. So cut, trim. Oh, was it that easy? I do believe it was. So now our little notch is a little lost lamb. Let's do vertical with this dot. Oh, that made it happy. And let's give it another angle. This with this. And that made that happy. Beautiful. Now, I don't want to copy all that 4 times. Well, this is just a test. That was easy, actually. All right, it's time to go bending. Stationary side. Hot dog. Look at that. I was right. It was totally right. Okay, so let's see if we can go back in time far enough to get that. Why did this not get mirrored? Darn it. I wonder if we can just select these and mirror them. Click mirror. So if we do newt, newt, newt. Those are the, no, that's not you. That. And yeah, I think that'll do. Let's do mirror line. Mirror line. We'll do the center line. See what happens. I'm gonna have to clean this up a hair. Yeah, we're gonna have to clean it up, but it's why is that weird? Yeah, we got all the dots there. It's close enough for now. Okay. Now we just need to go and do it again. Let's do a mirror again. We're into less familiar territory here, so this is now more exploratory surgery than educational content. So explore along with me. So now if we can trim this out and turn this into a construction line. Oh, we just trimmed that one. Delete toward. Okay, there we go. How did we dimension this? Oh, you know what? We can just do symmetry. These things. Oh, now they're dead. It's becoming slightly less fun. Or are they just selected? Nope, they're not selected. Do you want a length? Wouldn't imagine that would be it. Oh, don't crash. Okay, let's see. Oh, that's over constraining again. All right. Thank you. So you got a degree, but why is this not happy? That's weird. That shouldn't help it. So looks like maybe this dimension is not applied properly. No, that's fully constrained. This height? No, I don't know why. That, whatever. And this with this. Whatever makes you happy, Fusion 360. Whatever makes you happy. Oh, now this is happy. I wonder if that's about the mirroring. And this is mostly happy. Let's trim this out. Can I break everything? No. But this this needs to be not a construction line. Mysteries. I don't think it's been done up here. No. And that randomly has gotten unhappy there. Let's make it symmetry. Why not? Whatever. I'm gonna mirror this over there. This is all slightly frustrating. Is there a real line there? We'll find out. I don't think there is. That line is construction line. Is there another one here? Line. 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 There we go. That's happier. Let's try and mirror this again. See if if I knew this slightly better, as I get better at it, it will be less frustrating and puzzling, which is probably obvious. Oh, interesting. Actually, I may have done too much here. That might be the problem. Yeah, let's try that. Mirror line. Oh, yeah, okay. I think that's better. I think that's better. I wonder if I can symmetricize that. Or drive. Let's do a driven dimension. So this is D15. Let's see if we can just say this is the same as D15. A little inconsistent, I know, but and around here to learn. This is not necessarily a production part. D15. Effects, D15. All right, you're happier about that. What's the deal with this? Oh, there we go. Let's just re-D that. Over constraint. Whatever. Okay. You're happy. You happy down here? Looks like you are. Hot dog, I think we're ready to try and bend again. Let's save. Whew. It was kind of frustrating and tough. Slots added for bend. Yeah, I'm very curious what the other streaming platforms are up to here, how things appear on Facebook and YouTube. So pardon me, I'm just going to check, see if I have the ability to do that. So pardon me, I'm just, oh, that's loud. Okay. It is working on YouTube, clearly. Is my Facebook streaming? Yes, it is. I don't know how to tell how many are watching, but that's all right. It is working. Cool. We will see if we can bend this up, and then we'll call it a day at that point. Probably going to be around 2 hours at that point if all goes well. Before the stream ends, I'm going to peek at all of you people in the chat and see. I know, Tim, you're real, or Time, you're real, but the rest, who's a bot and who's not? It's more amusing than irritating. Nice to have an audience, at least of computers. So let's go bending. All right, we're going to create a, wait, what? Okay, so finish sketch. So I'm not too familiar with the timeline stuff. Okay, so let's do, like, I wish I knew how to expand the details out here. And I see the warning, and I want to just like delete that whole thing. But I don't know how. Let's just proceed as if none of that happened. Okay, so it appears to be that we are already thickened. And let's do our bending and see if that if this is fun and exciting. Come on. Come on. Oh yeah. Oh yeah. Look at that. Want to do that yet? Wait. Oh, what? Oh, okay, yeah. Whoops, that one doesn't like that. Doesn't like anything anymore. What? Let's just try to restart this flangey thing. It doesn't seem to be happy. Let me make sure all the bits and pieces are actually closed. You know, I don't think they are, because I think in the sketch it would appear blue, solid blue. Does it? No, damn it. It doesn't. Something is open. Oh, what a pain in the ass. I'm pretty certain we broke it on one of these corner bits. There. There. Ill. Cross fingers. Yes, yes, yes. We gassed right. Okay, finito on the sketch. And it's happy. It's happy. It's no longer yellow. It's not erroring. Beautiful, beautiful. Let's go bending, shall we? Everybody's bending now. When somebody sneezed. All right, big reveal time. As they say in the blender industry, will it bend? Nope. But we're on our way. Okie doke. Yeah. Look at this. Turn our sketches off. We got a bentish box, a bentish box. See, it automatically kind of curved the corners. How did our little gap do? Yeah, it's tight. Yeah, it's interesting. Yeah, that might be the problem. Like it might actually want a diagonal here to know how to do the curve. Or we might want to put a circle relief out there. Do I bother to troubleshoot that today? I don't think so. Well, let's do 5 minutes of troubleshooting. See what we can get. Let's go poking with bending again here directly. Stationary. Oh, no, that's wrong. This we want stationary. And we want body would self-intersect. Try increasing bend radius or reducing bend angle. Use flip button to quickly change bend direction. Oh, let's see if it'll bend the other way. No, it will not. So bend, what did it say, bend radius? Would self-intersect. Try increasing bend radius or reducing bend angle. There's radius. That's angle. How do we change the radius? Override rules? Doesn't want to do that. Let's change the radius. Let's just see 40. I don't even want to do 40. I would like 10. Nope. 1? You give me 1? You give me 1. All right, well, what's the difference here? Maybe, are we bending on the wrong point? Oh, no, I feel like that's the right part to, oh, well, maybe, I don't know. What is our problem here? Let's keep increasing the bend radius so that we can, till we get find out where our error is. 5 degrees. Oh, you'll do 5, 9. Did you like 10? You didn't. She likes 9. Let's see what's going on beyond 9. Yeah, I think this might have to do with the fact that it doesn't know to put a big circle or something here. You see, yeah, I'm pretty sure it has to do with that little bit. But look, we're getting there. Sees it tilting. Let's turn the sketch off. And oh, it also might be, these two curves might be hitting each other. This bend radius, where we, that was something we didn't see. This also, honestly, this also looks way thicker than they intended it. Can we edit that? Just thickness. That's it. Body. Properties. Steel. Ain't right. You know, that might be the source of our issue. Let's go Fusion 360 sheet metal. Change this. Hello. Modify sheet metal rules. Okay, so modify sheet metal rules. Not exactly what I would have assumed to be. Yeah, let's that ain't working. Edit rule. Oh man, this is whatever. Thickness 8/100ths. Let's just try 1. May give us some clues at least. 100ths. That's 10. Oh, it said it would. It might be 50 thousandths. Oh, anyway, we'll try this. Let's see if our bend works better with much thinner aluminum. Okay. Let's re-attempt our bend. Or do you want to be done with this? All right, let's try and cross the 10-degree barrier. 10. Hey, we got 10. Let's do full 90. Doesn't like that. Let's try 50. 70. 80. No. 75. Not 50. 75. 78. 79. 80. Nope. So we get 79 degrees. Let's see what's binding at 79 degrees. Hey, we're real close, folks. Real close. Oh no, I don't see anything binding. I mean, we see air between there. This might be prematurely cautious. Maybe let's fiddle with bend ratio. If we increase the bend ratio, maybe that will give us a wider sweep on the corner. Because I'm thinking it may be like this bit and this bit it thinks they're going to hit, or this bit and this bit, or this surface and that. We shall see. So let's make this maybe wider sweeping so that it puts this farther up. I think farther up. Oh, I don't think that's how that works. Oh, it's this. This is going to intersect with this. And then this whole bit is going to try and curve with this. That's it. We need to reduce our bend ratio, or yeah, make this curve tighter. Good job, team. Well, highly confident speculation that that's a good guess. Bend radius, thickness, tear, straight round, leaf width, depth. Making me do thinking here. Straight. It didn't seem to change what things look like. Oh, wait, what? Yeah, no, it didn't. Let's go over here. So, do that again. I'm gonna have to corner conditions. Oh, literal corner conditions. Bend. Oh, relief. That's not what we're looking for. We're looking for bend radius is thickness. Well, thickness divided by 2. Give us a tighter. Oh, yeah. Still sharp curve there. All right. All right. Here we go. Let's test our bending. Can we get 90? Yeah, fuck yeah. We guessed totally right. Right at the 2-hour mark in our stream. Let's go ahead and finish the bend here on this one. And we'll call it a day. I had fun, team. This was good. Learned a bunch. Stationary side. Bend line. Look at that. Look at that. Our pretty little box. Well, that ain't pretty. Pretty utilitarian. Looks like a Radio Shack project box. And it's got some, I wonder if we can change the thickness and make this look less goofy here on the edges, now that we've thinned up our radiuses. I don't think it likes that. Yeah, does not like that. Two. Still doesn't like that. We're going to go back to 0.1 inch thick. Good enough for today. Good enough. I like it. Let's save. All right. Thank you, everybody. I appreciated all of your presence here. Follow on Twitter, Instagram, Facebook, Twitch, BalloonSciDan, at BalloonSciDan, for more content like this. Also, lots of balloon document snippets posted on Twitter and Instagram, pretty photos and things. And please consider supporting on Patreon. That's what allows me to do this stuff and even more. Eventually I'd like to actually start doing educational content that's more extensive in experiments too. So patreon.com/balloonscience. And we already have a bunch of patrons as seen here down at the bottom of the screen. Mike Bowen, Sheila Bunch, Ben Lathan, Ken Howard, Sophie Searcy, M. Fong, Ashley Meyer, and Robert Quattlebaum. Thank you all. And good day/night.